Welcome to the lecture series on CFD Part 1. This is Lecture 3 on governing equations and their properties. Before we start with basic finite difference approximations in the next lecture, we shall first discuss in this lecture the main features of the various forms of equations that serve as mathematical models for flow simulation. I'll first describe the conservation laws for mass, momentum, and the generic scalar quantity, and show how are the conservation laws transformed from control mass to control volume form. I will then present and discuss differential, vector, also called coordinate-free, and integral form of the conservation equations for mass, momentum, and generic scalars. The difference between conservative and non-conservative form of equations will be described next, followed by the presentation of various forms of the dimensionless equations. The lecture is closed with a brief summary of implications of the various choices on the properties of the numerical solution method. The laws of motion are defined using control mass approach and extensive properties like mass and momentum. Bodies are followed along their trajectories, which is known as the Lagrangian analysis approach. This approach is not suitable for studying fluid flow. We are not interested in the motion of any particular fluid particle, because millions of them come and go with only a short residence time within the region of our interest, for example in a pump or turbine or in the vicinity of a flying body. We want to know what is happening in a particular space over a particular time period and how are intensive properties, for example density and velocity, varying. This is known as the control volume or Eulerian analysis approach. The mass conservation law states that the mass of a body does not change as it moves along its trajectory. The momentum conservation law states that the momentum of a moving body is changed by external forces acting on the body as it moves along its trajectory. The time derivative which describes the change of some body property along its trajectory is denoted by the Roman letter d. The relation between extensive, denoted here by a capital letter phi, and intensive properties, denoted here by a lowercase Greek letter phi, is defined by this relation. Note that the volume integral is taken over the volume of a control mass. That is, within this volume the same matter is contained all the time. There is no inflow or outflow from this volume. You can imagine wrapping instantly a certain volume of fluid with a thin membrane which does not offer any resistance to deformation, but which sticks to that particular amount of fluid as it moves and changes its shape. We need to express the rate of change of extensive properties along their trajectory into the rate of change of intensive properties at a particular point in space. This link between control mass and control volume analysis approach is given by the Reynolds transport theorem, which is mathematically expressed by this equation. Here ρ is density, v is the fluid velocity vector, Vs is the velocity of the control volume surface S, and n is the unit vector normal to the surface and pointing outward. Note that the volume integral on the left-hand side is applied to the volume of the control mass, while the integrals on the right-hand side are applied to the control volume through which fluid flows, but which may also arbitrarily move. The time derivatives on the two sides of the equation also have a different meaning, although they are denoted by the same letter d. On the left-hand side, the time derivative describes the rate of change within the control mass along its trajectory, while on the right-hand side, it describes the rate of change within the control volume along its trajectory, which can be arbitrary. Note that if the control volume moves so that it at all times coincides with control mass, that is, the same matter is within control volume all the time, then the surface integral on the right-hand side becomes zero, and the two time derivatives then have the same meaning. If the control volume does not move at all and remains fixed at the same location, then the velocity Vs is equal to zero. In this case, the time derivative on the right-hand side attains another meaning. It becomes a local time derivative, describing the rate of change in time at a fixed point in space. This is denoted by the symbol partial instead of letter d. This figure here shows at time instant tn coinciding volumes of control mass and control volume. The latter is fixed in space and thus stays at the same location, while the control mass moves on with fluid velocity. The first term on the right-hand side is related to the difference between content within volumes V1 and V2 at time Tn plus 1 and the same volume at time Tn, while the second term represents the net flux through the control volume surface. In the rest of this lecture, we shall assume that the control volume is fixed. Moving control volumes will be considered in the second lecture series. Let us now have a look at different forms of the mass conservation equation, which is often called the continuity equation. The integral form of this equation follows directly from the Reynolds transport theorem when phi is replaced by unity. The rate of change of mass within control volume is balanced by the net flux of mass through the control volume surface. The integral equation is valid for any control volume, no matter how small or large. When we sum up equations for all control volumes, all inner surface integrals cancel out. There remain only integrals over solution domain boundaries. By allowing that control volume becomes infinitesimally small and using the Gauss theorem to convert the surface integral on the right-hand side into volume integral, the integral form of the mass conservation equation can be transformed into this vector or coordinate-free form. By introducing the appropriate definition of the divergence operator in a particular coordinate system, we can obtain the differential form of the equation expressed via these coordinates. Here, the differential form of the mass conservation equation in Cartesian coordinates is given. We shall see later the equivalent form in polar cylindrical coordinates. The momentum equation is substantially more complicated than the continuity equation. First of all, momentum is a vector quantity, and therefore the momentum conservation equation is a vector equation. To solve it, we have to split it into three equations for velocity components in a particular coordinate system. The left-hand side of the equation is similar to the left-hand side of the continuity equation, but because now phi is equal to the fluid velocity vector v, a tensor vv appears in the convection term. On the right-hand side is the sum of forces acting on fluid within control volume. Which forces are present depends on the particular application. For realistic fluids, shear and pressure forces are always present. They can be expressed by the stress tensor T, given here. P is the pressure, mu is the dynamic viscosity of the fluid, I is the unit tensor, and D is the rate of strain tensor, defined by the velocity gradient and its transpose. Gravity is the usual body force acting on the fluid. The momentum equation in integral form looks then like this. The vector or coordinate-free form of the momentum equation for the velocity vector is given by this equation now. By introducing the appropriate definition of the divergence operator in particular coordinates, we can obtain the differential form of the equation expressed via those coordinates. As already mentioned, this equation needs to be split into three equations for the velocity vector components. The problem is that conservation of a vector does not imply conservation of its components. Vector components depend on base vectors, and only when base vectors are not changing are components automatically conserved if vectors are conserved. The problem is illustrated in this figure. The velocity vectors at location A and B are the same, indicating the conservation of momentum when no external forces are acting on fluid. Shown are also Cartesian and curvilinear coordinates and their corresponding base vectors, Cartesian, contravariant, and covariant. Only the Cartesian vector components are the same at points A and B, when vectors are the same. The other components differ because of changing orientation of coordinates, even if vectors stay the same. Here is an easy-to-follow example. We consider a uniform fluid flow without action of external forces so that the velocity vectors are the same in the whole two-dimensional flow field. Assume that we have chosen to do a numerical simulation of such a flow using governing equations expressed via polar cylindrical coordinates and base vectors. Of course, this is not what we would normally do, but still it is a valid possibility. In this case, the velocity vectors are the same at points A, B, C, and D, as well as at any other point in the flow domain because the flow is assumed to be uniform. However, in points A and C, the circumferential components are equal to 0, while at points B and D, the radial components are equal to 0. The radial components at points A and C are of an opposite sign, as well as the circumferential components at points B and D. At the coordinate origin, the vector components are singular, although the vector is not changing in any direction. The changes in velocity components are only due to the changes in the directional coordinate lines. The momentum equations for velocity components must contain terms which cause this variation. These are the apparent body forces resulting from coordinate transformation. To avoid such problems, in most commercial and public CFD codes, vectors and tensors are expressed via their Cartesian components. The equations for Cartesian velocity components are obtained by taking the dot product of the momentum equation for velocity vector with Cartesian base vectors II. The integral form of the equation for velocity component II is given by this expression. This equation represents the vector or coordinate-free form. The vector Ti results from dot product of Cartesian base vector II with the stress tensor T, see slide 8. Here it is presented as a function of velocity gradients, dynamic viscosity mu, and pressure P. The viscosity-dependent part is usually denoted by tau. The differential form in Cartesian coordinates is obtained by implementing the Cartesian form of the divergence operator shown here, with an example of its application to the velocity field into this equation. This leads to the equation for ui, which is here written in tensor notation using Einstein's summation convention. When an index appears in one term two times, like here j and j, this implies summation over the range of indices. Thus, this convection term here stands for three terms. In one, index j takes the value 1, in the other 2, and in the third 3. Index I appears only once in each term. It determines for which component is the equation written. The convection term is said to be in a strong conservation form when it is expressed as a divergence of a vector quantity. By using rules for differentiation of products of variables, we can split this term into two terms, shown here. If you do the same with the rate of change term, that is, express this term as rho times time derivative of velocity component ui plus ui times the time derivative of density, two terms can be grouped together as the product of velocity ui and the left-hand side of the continuity equation. The continuity equation is shown here. Because the right-hand side of the continuity equation is 0, these terms drop out of the momentum equation. Thus, the conservative form of the momentum equation for velocity component ui can be transformed into the non-conservative form given by this equation. The conservative form of pressure term, which is here embedded in the vector Ti, can be expressed in a non-conservative form as a dot product of the pressure gradient and Cartesian base vector II, which gives the pressure derivative in xi direction. From the mathematical point of view, both conservative and non-conservative form of the momentum equation are fully equivalent. No approximation is introduced by the above transformations. However, the conservativeness property of the numerical solution method may be impaired by using the non-conservative form, especially on coarse grids. The Navier-Stokes equations, that is, the continuity equation and the three momentum equations for velocity components, are listed here for the polar cylindrical coordinate z in axial direction, r in radial direction, and theta in circumferential direction. When the flow is three-dimensional, there is no reason to use any other form but Cartesian because it results in the simplest form of equations. However, in some applications, under certain conditions, a flow which is three-dimensional in Cartesian coordinates becomes two-dimensional in polar cylindrical coordinates. Reducing the dimension of the problem from 3 to 2 results in huge savings in computing effort, which is why axisymmetric problems are still sometimes computed in a polar cylindrical coordinate system. We shall not go into details here. I only want to draw your attention to the fact that momentum equations for the radial and circumferential velocity component now contain terms which are not differentiated. They are framed in red here. These terms act as apparent body forces, that is, source or sink terms for the corresponding variable, and are responsible for changes in velocity components that arise solely from the change of coordinate and grid line direction, and have nothing to do with momentum conservation as discussed in slide 10. These expressions represent viscous components of the stress tensor expressed in polar cylindrical coordinates. One non-differentiated term is present in stress components too. See the frame term in red. All conservation equations have a similar form. They contain the rate of change term and convection term on the left-hand side and diffusion and source terms on the right-hand side. It is therefore customary to explain all steps related to discretization and solution of algebraic equation systems on a single generic scalar transport equation and only later explain the specialties of momentum equations. The integral form of the generic scalar transport equation, which serves as the starting point for finite volume method, is given here. The left-hand side is the same as in momentum equations for velocity components when ui is replaced by variable phi. The diffusion part on the right-hand side is simpler than in momentum equations. Diffusion of scalars is usually described using gradient diffusion hypothesis, known as Fourier law for heat and Fick's law for species diffusion. Therefore, we have here the diffusion coefficient gamma, which may be constant or a function of temperature, concentration, or other variables, and the gradient of the scalar phi, whose dot product with the unit vector n, which is normal to the surface and directed outwards, represents the derivative of phi in the direction of unit vector n. This term represents the sum of source and sink terms within the control volume. The corresponding vector form and differential form in Cartesian coordinates are given by these two equations. The conservation equations can also be written in dimensionless form. To this end, one needs to select the reference quantities by which time, length, velocity, pressure, and temperature are to be normalized to become dimensionless. Thus, one has to select the time scale t0, length scale L0, velocity scale V0, and temperature scale T1 minus T0. In simple flows, it may be obvious which quantities should be used for normalization. For example, in periodic flows, time scale is the period. For a flow in a pipe, length scale is a pipe diameter, and velocity scale is the mean velocity in the pipe cross-section. However, in complex geometries and non-periodic flows, the choice may not be so obvious. When all variables are normalized as indicated here, the continuity equation, the dimensionless form of the momentum equation for the velocity component ui, and the equation for temperature are shown here. These equations contain four dimensionless numbers: Strouhal number, Reynolds number, Froude number, and Prandtl number. While Prandtl number is a fluid property, the other three dimensionless parameters depend on the flow and geometry as given by these expressions. Two flows are said to be similar if these four dimensionless parameters are the same under the same dimensionless boundary conditions. This is obvious because the solution of the dimensionless equations will also be the same in this case. Not only that the choice of normalization quantities is not unique, there are also other dimensionless parameters that can be more suitable for particular flow types. For example, for natural convection flows, momentum equations are often written in this form, given here. Here, Ra is the Rayleigh number, Pr is the Prandtl number, and Gr is the Grashof number, given by this expression here. The Rayleigh number depends on density ρ, gravity g, coefficient of volumetric expansion beta, temperature difference T1 minus T0, length scale L0, the dynamic viscosity mu, and the Prandtl number. And the Rayleigh number is equal to the product of Grashof and Prandtl numbers. Dimensionless equations are useful to analyze the order of magnitude of various terms. However, it is otherwise best to work with dimensional equations as SI units and present the results in dimensionless form where desired. Let me briefly summarize this lecture. There are over 70 forms of the Navier-Stokes equations depending on various choices like base vectors, coordinates, etc. They are all mathematically equivalent, but some are more suitable for CFD than others. The simplest form is based on Cartesian coordinates and base vectors. It is best suited for both finite difference and finite volume methods. Other forms of equations may be better suited for special problems. For example, when one dimension can be reduced to become two-dimensional instead of three-dimensional. Axisymmetric problems are often computed using polar cylindrical coordinates and base vectors. Non-conservative form of equations is sometimes used in finite difference methods for simplicity reasons. On coarse grids, this usually leads to larger errors than when the conservative form of equations is used, but when grids are fine enough, the differences are usually small. Dimensionless forms of equations show the relative importance of various terms and the dominant dimensionless numbers like Reynolds number, Froude number, Struhal number, and Rayleigh number, but it is usually safer to work with the standard equations and present the results in dimensionless form when desired.